What up, what up? This is the Cyber Tutor, and we are going to go into registers and register operands today. So I want to take a look at this little graphic I have here, just to talk about the structure of a general purpose register. So the registers that we have today are 64 bits. In the past, they were 16 bits. Let me see if I can write that here. So they were 16 bits, and we've also had 8 bits and 32 bits. So as registers in CPUs evolved over time, they got more space. And so today we can still actually break those registers into smaller pieces, those 64-bit registers. So let's say here that we have the register racks. Let me draw that. So this whole thing here is the racks register, for example. And so the racks register nowadays is 64-bit. It still has a name for the 32-bit and the 16-bit and even the 8-bit version of the same register. So here we want to call this AL. So this is the lower 8 bits of the register. AH is the higher 8 bits. And then together we can call this, let's see, here we can call that AX. So this is the AX portion of the racks register. And so specifically if you're referring to the lower 8 bytes, you can call it AL, upper 8 bytes, or where it hits 16 bytes, AH. Although this is not very commonly used. There's also a name for the 32-bit version of the register, or the 32-bit segment of the register, I should say, because it's more like taking the register and dividing it into chunks. So this one, we're gonna call that EAX. So when someone is talking about assembly language or kind of this low-level development stuff, if they talk about EAX, they're going to be talking about the 32-bit racks register. And you'll see that come up sometimes. Sometimes you'll even see it inside assembly programs when you're working with 64-bit registers. And the reason for this is because the registers evolved throughout history. So 16-bit computing, this goes back to the 1950s. Over time, we ended up extending those registers into 32 bits, and then eventually extending them, as you know, into 64 bits. So registers that are used in the 64-bit instruction set are actually just supersets of the older registers. So that's kind of what I was talking about earlier when I was talking about opcodes, how I said some of the shorter opcodes are like more like the OG opcodes, and then the longer ones are supersets of the smaller ones. So this same naming convention also works with other registers, not just racks. For example, the the base register, so RBX, the lower 32 bits of that would be EBX, the lower 16 would be BX, and then the lower byte would be BL, and then BH is the second byte. So it's kind of almost the same as racks, how it's set up, but you would say BL, and then you would say BH. So that naming convention kind of just stuck as they were adding more and more space onto the CPU registers. I also want to go into the different types of registers, because I think that that's probably the most important thing when you're learning low-level assembly language and binary analysis. You have to be able to look at those registers and just know right off the top of your head what the registers are and what they do. You don't have to know all of them at first, but getting an understanding of at least the general purpose and then sort of a general idea of what the other types of registers do is very important. So now I want to cat out this note file that I have talking about the general purpose registers and other types of registers and what they do. So I made this extremely simplified, very oversimplified, just to make it easier. So these registers here, if you don't want to learn about any other registers yet, I would just learn about these because these are the most important. The general purpose registers are the ones that you're going to encounter a lot. So, fun fact about general purpose registers is that in the past, a lot of these had specific functions, which is where we get the names of the registers. But nowadays, in 64-bit computing, we can actually just use these registers for all kinds of different things. They've become more general purpose registers. So you can technically kind of just use them all interchangeably. Although in practice that doesn't necessarily happen, but it is possible. So the first one that we have is racks. So this is the one that was used in the book as an example, and again in my example. So racks, the accumulator, this is used for arithmetic operations, stores function and return values. It's used in multiplication, division, and system calls. So a system call is when your program wants to talk to the operating system and ask it to do something. Then we have RBX base. So this is a general purpose storage register. Historically, it was used as a base pointer for memory addressing. This is for like older types of addressing modes, but it's not really used this way today. Again, as I was saying, you can kind of use this for anything because that's just what it's like now in 64-bit computing, although it wasn't in the past. Then we have the counter, which is RCX. So this is used for things like loops, if you've ever done programming. So it counts iterations. Let's see, RDX. RDX is a data register. So this is used for input-output data operations. It can also be used in division and used to pass the third argument to functions. Don't worry about what that is. Stack pointer, RSP. So these two are interesting. I spelled that wrong, apparently. These two are interesting because they're used in something called a stack, which is a data structure that programs use. We'll talk more about that in depth later. But basically, the stack pointer points to the top of the stack, and then the base pointer, you can kind of see how they go together with RSP, RBP, so they both end in P, pointer. That points to the base of the stack. And then you have the source index. So this is for string and memory operations. That one, I think I won't go into that either. The destination index, RDI, so that is also, that is a destination pointer also for string and memory operations. A good way to think about RSI and RDI is when you're copying files. So like, let's say that you want to copy a picture from one folder to another. So the RSI could hold the path to the source folder. So if you say like, open, folder, picture.jpg. So that would hold the path to the actual folder that you want to open. And then the destination is like, if you want to copy and paste it, the RDI would hold the destination where you could paste it. So I think that's a good way to think about it, in a way that's not as technical. So then after that, we have x86-64 general purpose registers. And remember what I said before, that we just use x86 as the catch-all term, but x86-64 is referring to registers that are just used in the 64-bit version of the architecture. And so these are general purpose R8 through R15. So if you see R8, R9, R10, etc., you can know that these are 64-bit architecture registers that are not used in previous versions of the assembly language for Intel x86. So, and then we have other registers. So there's RIP and there's R flags. RIP is the instruction pointer, And I want to read something out of the book for that because I feel like it explains it very well. It says, the instruction pointer always points to the next instruction address and is automatically set by the CPU. You cannot manually write it. On x86-64, you can read the value of the instruction pointer, but on 32-bit x86, you cannot even do that. So as you can see, this register is very locked down. That's why we do not consider it a general purpose register, even though it kind of, in a way, when you look at how it's written, kind of follows that format, but it would not be considered general purpose because you can't really manipulate it in the same way that you can a general purpose register. So this is always following the instructions. So when you're stepping through your program, this register is always going to have what's next. So not what's currently executing, but the next thing. That's always going to be where RIP is. Then we have R flags. So R flags is kind of like a status register. So this is used for comparisons and conditional branches and tracks things like whether the last operation yielded 0, resulted in an overflow, and so on. So R flags is just kind of giving you information about the results of the calculations that the registers are doing. So it's pretty easy to remember this one because you can just think flags. So after it calculates something, it can throw up a flag to indicate that there may be some kind of error, or there was an overflow, or something like that. So I decided to go back and give a little bit better of an explanation of what the segment registers do. So the segment registers, they are not used as extensively in the 64-bit version of the x86 instruction set as they were in previous versions of the instruction set. So you might not really run across all of these when you are doing reverse engineering. So you'll see them all if you're using something like GDB, but what you might notice is that only a couple of them might have values in them. So I'm just going to talk about 2 instead of talking about all of them. So first there's the CS, so that stands for code segment. So this basically just tells the CPU where is the program's code currently. So what is the location of the program's code? And then the other one I want to mention briefly is called SS, so that stands for stack segment. So this tells the CPU where the stack is at the current moment. So then we have control registers. These are used by the kernel only the kernel can access them, therefore they're not general purpose. They control the behavior of the CPU. So for example, if you want to switch between protected mode and real mode, you can do that with these registers, or rather the kernel can do that with these registers. So then finally we have the debug registers. So these are very helpful for what we're doing, which is binary analysis. If you've ever used a program called GDB in Linux, you might know what these registers are. So these provide breakpoints in your program. So basically when you run a program, actually, you know what? Let's just run a program. Let's see. So we can run, I think we still have a hello world. Yes, we do have a hello world program. So let's compile that quickly. Let's run it. A.out is the default output, but let's run it with GDB. So this is a debugger. Looks like we don't have it installed. So let me just install that quickly. Kind of silly that that's not installed, but it is what it is. So I have here A.out, which I compiled from hello world.c. So I just did gcc hello world.c, and that just automatically fully compiles that program, and the default output name is A.out. So I can do gdb A.out, and that will put our program into the very simple debugger that comes with Linux by default usually, although oddly it didn't come with Kali, so I had to download it. But so we can do info functions, so that will give us information about the functions that we have in this very, very simple program. As you can see here, we have puts in our function, which that was the interesting one that I told you how we wrote printf in the program, the hello world program, to output the text, but the compiler translated that actually into puts. So you can see here, we don't see printf as the function, we see puts as the function. So I'm going to break it at main, so I can just say break main. And then it says here, I created a breakpoint at a certain memory address. So that's where these debug registers will come into play, is at this breakpoint. So that's actually what gives me the breakpoint. So then I can run it, and I automatically reach the breakpoint because we broke it main, which is the first function and one of the only functions in that entire program. So then we can do info registers to see what values are in the registers when we broke it main. But as you see here, it's interesting because we actually don't see those registers, because if we go back, these debug registers are DR0 to DR7. So oddly, where would they be? We might be able to find them. So if we do info registers, let's try DR0, DR1, DR2, DR3, DR6, DR7, just for good measure. Let's do that. Invalid. So that's interesting. So why might that be happening? We might not have permissions to actually use them. So let's quit really quick. Let's move into super user mode here. So we've got root access. All right, awesome. So now we are root. So let's try running GDB as root and see if we're able to see those registers. Let's do the same thing again. Info functions, we can see here, same thing. We've got main, so let's break it main. And then let's run that. Okay, we're broken. We're broken. And then let's do info registers. Nope. Okay, info. Oh, we got something here. Oh, no. Because this is, even though it starts with D, that is a segment register. And so, interestingly, we do have something inside the segment registers. So let's try it again. Let's try info registers, DR0, DR1, DR2. Same thing we had before. Invalid. So these registers are very real, but they are super, super locked down. So it can be very hard to view them. And if I find a way to view them, I will let you know. But I do not for now. So we can move on from there. So the sort of the sub-last thing is we have model-specific registers, MSRs. So you can get information on those by doing a command called CPU ID. So the results of this are usually insanely huge, so I won't do it here. But if you do that, you can get more information on model-specific registers, which are registers that just come with the specific model of your CPU. Then we have these 64-bit extended instruction sets. So there's SSE and MMX. We won't go into that either. These are not on all CPUs, although they will become relevant later. So now we want to talk about memory operands. So memory operands, I'll read from the book here, specify a memory address where the CPU should fetch one or more bytes. So you're basically telling the CPU, okay, go to this address, get the information from that address, and then put it in a register, and then move it somewhere else. So you cannot take bytes from one location in memory and just move them directly to another location in memory. You have to go through a register. It is mandatory, it is required, there is no other way to do it. The register is kind of like the brain cell. So the register is, it's kind of like the tunnel that you're going through. So like if you have one train going from one destination to another destination, you can't just like teleport through the mountain. You have to go through the tunnel. So the tunnel would be kind of like the register. So the register is processing that. So you have certain memory operands on x86 processors. So let me show you a formula here. We have base plus, place plus index times scale plus displacement. So this might look familiar to you because, let's exit this here. Let's go back to Kali user. Okay. So this might look familiar to you from the last lecture. So I'll open this as a file so we can see it. Just put it over on top of that. So if you remember this, I said dis for this diagram because I was running out of room, although I probably could have fit it, but this is displacement, remember? So this is a part of the instruction. So we had the prefix, the opcode, the mod reg rm, the sib byte, and then the displacement, and then we had the immediate. So this is where this becomes relevant, the sib here and the displacement. So the way that we calculate these memory addresses, the way that sib works, and the way that the displacement works, is that it's following this formula. So when you want to go find an address in memory and you want to get the data out from that address, you would do something like, for example, that's going to do nothing because it doesn't understand this command because it's not a command, it's just me typing. So an example is you could do move EAX dword pointer, and then let's do racks times 4 plus array. So this is an example of an operation that is saying move into EAX. So in this case we're using, right, EAX, which is here. So this is the 32-bit version of the instruction. You could also say move into racks. You could say move into AX, although this, the smaller you get, the less information it's able to hold. So if you have a lot of information, you might not be able to fit it in there. You can't cram 64-bit information into an 8-bit register, of course. So this says move EAX, and then it says move dword pointer. So a dword is another kind of a nickname for a data structure. So a word is, you know what, let me do this. I've got a little, there we go, word sizes. So a dword is 4 bytes. So this is basically saying move into EAX a dword. So we don't know where the dword is. This is where the dword is. But because we don't know where the dword is yet, all we know is that the dword is 4 bytes. So it wants 4 bytes of information, and it wants to, in Intel architecture, because we always go backwards, it wants to move that into EAX. So let's see this again. So move into EAX a dword, so a 4-byte piece of information, and then pointer. So this is interesting. So a pointer is going to point to a location in memory, and then we've got the formula here for what that location is in memory and how we can actually find it. So in this case, it's saying racks times 4. So because of the order of operations, we're always going to do multiplication first. So we're going to multiply racks times 4, and then we're going to add this array. So this is the beginning of an array, or in other cases, we could actually get even more specific than that. So we can do, let's cat memory operands and take a look at that. So here's an example of another memory operand finding a location in memory that's similar to the one that I just showed you. So Again, we're using that same formula, base plus index times scale plus displacement. So here's a fake instruction. Move into EAX. So again, we have the same thing. We have, oh, there goes my window. Put that back. So again, we have dword pointer. So it's move into EAX, a 4-byte piece of data. And then pointer. So we want a dword pointer. So a 4-byte pointer. And then RBX plus RSI times 4 plus 8. So base plus index times scale plus 8. So we have to get the location of RBX. So let's assume that we have that. So let's say that that's at OX 1000 in hex. And then we would multiply that by 4. Oh, sorry. We would add that to RSI multiplied by 4. So let's say RSI is 3. So let's say we have these two initial values here, RBX and RSI. But again, order of operations, we want to do RSI times 4 first. So we would calculate RSI times 4, order of operations, and that would become 12 because we've got 3 times 4. RSI is 3 equals 12, easy. Step 2 would be adding that to the base address. So again, we're adding that in hex. So in hexadecimal, 12 would be OXC. We want to add that to the base. So again, base plus index times scale plus displacement. So that would become OX 1000C. And then step 3 is add the displacement. So the displacement part of this opcode is saying, okay, so we want to, let's say we want to do plus 8, right? Because our displacement here is plus 8. So that would become OX8, and then OX8 plus OX100C. In hexadecimal would be OX1014. So the result of our answer is OX1014. So then that would end up going back into EAX. And that would be the end of our memory operand. So the SIB byte, which is what we mentioned earlier and said we weren't going to mention until later because it's got this weird way of calculating stuff. So this is exactly what the SIB byte does. So this is exactly how the SIB byte calculates the location in memory in order to retrieve data from it. So SIB stands for scale index base. And as you can see in this formula we have base plus index times scale plus displacement. So that's exactly what that stands for. And displacement, of course, is self-explanatory. So the last thing that we want to talk about is what the immediate does. So that's the very end of the operand. So the immediate can be anything from 0, 1, 2, or 4. So the immediate is, actually, we can show an example of what the immediate is if we cat out our hello world.s program. So the program that we compiled, but we did not assemble it. This is the assembly language before it gets fully compiled. So this program that we created actually has examples of immediates. So an example of an immediate might be move EAX 0 or sub RSP 16. So this part here, the 16, this is a hard-coded value. And so because it's hard-coded, this is what the immediate is responsible for. Immediates are encoded in little endian, so meaning the least significant byte of the integer comes first. That is something that you can look up and read more about. There's big endian and little endian formats when we're talking about this CPU architecture. So yeah, so basically I think that's all you need to know for now, is that these values here, this is what the immediate is in charge of.